In section 112, we're going to work some more on solving systems of linear equations using algebraic methods. So we're going to use both the substitution and addition method. We already did the substitution method in section 111. We're going to do it more in this section in a few additional contexts. The way we set up these questions in this situation is going to be different. Some of these are going to involve parentheses, and we shall see how they go. All right, so in this scenario, we are serving on a committee responsible for buying fireworks. The first thing we learn is some terminology. There's a couple types of fireworks. There's cakes, which are single fuses, and there's peonies that look like spherical balls in the skies. So we're going to be put in charge of purchasing fireworks. We need a total of 30 fireworks to cover our time frame. And peonies cost $44 each. Cakes cost $47 each. My budget is $1,350. I want to figure out how many cakes and how many peonies we could purchase and still fill up the time required. So if I bought, all of one kind, I might not be able to spend the total. So I need to mix it in to try to get all the budget all the time. Okay, so two equations. First of all, I'm going to try to buy 30 fireworks. And so my fireworks, I'm going to call cakes and peonies C for cakes and P for peonies so I can keep straight my variables. C is cakes, P is peonies. I need 30 fireworks. So the total number of cakes plus the total number of peonies I buy has got to equal 30. Otherwise, I'm already screwed. I have to have 30 fireworks. So C plus P is 30. Also, though, I got to make budget. Each of the cakes costs $47. So every cake I buy is $47 plus every peony I buy is $44. And that sum of their costs, cost of the cakes, cost of the peonies, can't be more. It's got to equal that $1,350. Oh, I wasn't reading my directions, and they wanted me to write this equation down here instead of both of them up there. I got on a roll. So we got both our equations. One is for the number of fireworks, got that. One is for the budget, got that. And then they're like, just in case you couldn't get it, there's the two equations. Okay, so next, solve each of the equations above for P. Now, I would not like to do that. So scratch this. We're going to do it my way instead. Because it's better because what I want to do, they're trying to make it look just like it did in the previous section where I had C equals or P equals for both the equations. I could plug one P in for the other. That's going to create a nasty fraction though when I divide this 44 off. There's no reason to do that. What I want to do is solve not each, but solve one of the equations for P. So that I will do, solve one of the equations for P. And does it have to be P? No, it could be C, but we'll just choose to do P this time. You can pick. In this equation, either of C and P are equally easy to solve for, so I could really choose which of the two I wanted. So let's do P. So C plus P equals 30. Solve it for P. So minus C from both sides. All right. So that's going to put our P by itself, and it's going to be equal to 30 minus C, or negative C plus 30, doesn't matter how you phrase it. Okay, then the substitution step. So what I'm going to do here is I know what P is equal to. I'm going to plug it in where P is. So I don't have to have this P by itself. Just plug this in where the P is there to save from fractions, because who wants them when we don't have to have them? Let's not introduce them. So I'm going to have 47C plus 44P. Okay, but P is this whole quantity now of 30 minus C, and then we have our equals, our 1350. Okay, I need to do a distribute here. So 47C plus, wait, hold on, I forgot to do that multiplication. I started writing, I don't know what 44 times 30 is, so I better figure that out. We need to take 44 times 30, 1,320. So 1,320 minus, and then 44 times C is 44C equals 1350. Okay, combining like terms, 44C minus 47C minus 44C are on the same side, so we'll just subtract them. 44, can't talk. 47 minus 44 will leave us with 3C, plus the 1,320 equals the 1,350. Now that the equation is simplified, we did the distribute, we did the combine like terms, we're ready to move things to the other side. Moving to the other side involves the inverse operation. So because this 1,320 is positive, I'm going to subtract it from both sides. And I'm out of room, so we're going up here. 3C. And then equals, that's going to be 30 when you finish that subtraction, and then you can divide both sides by 3, and we get C equals 10. We're not done yet because I have to know both variables before I finish solving a system. I know C is equal to 10, and I could plug 10 in for C in either one of my equations, and I could solve for P, but I also have this new option in the equation that I've already solved for P for. That's probably my best choice, just 6C in here. So I know that P is going to be 30 minus C, or 30 minus 10, so P's got to be 20. Even if they don't ask me, always interpret. So I need a quick sentence. We need to buy 10 cakes and 20 peonies. All right, that's our goal here. That was accomplished with the substitution method, where I solved for one of my variables, substituted what it was equal to into the other equation. Let's say we're going to start the addition method next, and hopefully do the same question with the addition method. No, they do it for me, but I get to do it again at the bottom. Got it. Okay. So they go through the addition method here, and they ask us in the addition method to multiply both equations by whatever it takes to get rid of C. Since there are 1C and 47C, we're going to multiply this by negative 47C to get those to add to 0, because we certainly don't want to create more variables. Like, don't do that. Get rid of a variable so that you can solve for a variable. So in the addition method, step 1 is lining up the equations vertically. If necessary, multiply one or both equations by constants so the coefficients of one of the variables are opposites. Then add the equations together to eliminate one of the variables and solve the result. Okay, so we're going to work through it similar to what was shown up above, but we're going to get rid of the other variable just to show it doesn't matter which variable you get rid of. They got rid of C. Well, let's get rid of P. Okay, so P. There's our P, there's our P, there's 44P, and I know that for P's, I'm looking for the least common multiple. What can I make both of those go into? So 44 is it. So I'm going to multiply this top equation by negative 44, everything, so that I can get a negative 44P here to add to this negative 44P there. I know I'm not going to have enough space, so I'm going to start in my margin. Negative 44C minus 44P equals, I got to find out what 44 times 30 is. Oh, I already know. Conveniently, it's 1320. Negative this time, though, right? Negative because it was a negative 44 this time. All right. Then underneath, I don't change because I already had a positive 44 in the bottom equation. So I just write it down. And when we add these two equations up, P is going to eliminate because negative 44P plus 44P is 0P. Negative 44C plus 47C is 3C. Negative 1320 plus 1350 is 30. Divide both sides by 3, and we have C equals 10. As you can recall from the last page, C was supposed to be 10, so we're on the right track. Now we got to find P. I don't have it solved for yet, so I got to go into one of the original equations. No one's going to want that bottom one because the numbers are big, so you could choose the top. So let's go for the top. 10 is C plus P equals 30. So subtract the 10 from both sides. P is 20. And again, 10 cakes, 20 peonies, Write that down. All right. Now, note at the bottom, not all systems have convenient coefficients, so sometimes we need to multiply both the equations by something in order to get them to be additive inverses or opposites. So we'll do that in this case. So I'm going to examine these and think about the x's. So for the x's, I needed to multiply to make them both the same number. So I want to know what number 2 and 3 both go into. What's the smallest number that both 2 and 3 go into? So it's 6, right? And then for the y's, what's the smallest number that 2 and 5 go into? So that's 10. So I could work this through with getting the x's to both be 6s or the y's to both be 10s. It doesn't matter which one I do. I get to decide. And usually I would choose the one that had the smaller number to work with, because the bigger the numbers get, the harder they are to work with. So I'm going to get rid of the x's because they have a smaller GCF, smaller least common multiple, I meant to say. So it doesn't matter. 6 and 10 are relatively both small. But if one of them was like, 6 and the other one was like 312, 6 has a clear advantage. Okay, so let's say we're getting rid of x. So we're going to have to make these both 6s. And I don't want both positive 6s. I want one positive 6 and one negative 6. So first things first, I'm going to write down my two equations. I'm going to use the margin because I know I can't squeeze it in that little bitty space. Just writing down my equations. All right, now I need to know, what do I need to multiply by to get a 6? So I've already got a 2, so I need to multiply by a 3. And I'm going to make sure that that 3 distributes to everything. That's going to actually cause not a 6, but a negative 6. So my other one needs to be positive 6. So I'm going to use a 2 here and multiply every single thing by that 2. And then I'll have a negative 6 and a positive 6, and my x's will eliminate. So that sounds good, and we'll do it. So top line, that's going to be negative 6x plus 15y equals negative 48 from that 3 times 16. Bottom line, 2 times 3 is 6x, 2 times 2 is 4y, 2 times 5 is 10. Add up your equations. I'm adding these, so negative 6x and 6x adds to 0. This is going to be 15 plus 4 is 19y. This is going to be negative 38 from negative 48 plus 10. We're getting there. We need to divide both sides by 19. And if I divide 38 by 19, negative 38 by 19, I should get negative 2. And you can double check if you are not sure on this one. I know that one's probably not a common multiplication fact. So you can take negative 38 divided by 19. And as you see, we get negative 2. Half done. So I know one of the variables. I know the y. I still need to find the x. So y, I can plug in either one. I'm just kind of looking to see which of the ones I like the numbers better. I like the bottom numbers better because they're littler and they don't have negatives. So I think I'm going to choose that one. So 3x plus 2y, which is negative 2, equals 5. So that's 3x minus 4 equals 5. Add the 4 to both sides. 3x equals 9. Divide by 3. X is 3. So my answer, I got to read my steps here. I did all of this in like the margin. I could have done it in a couple of these spaces. But we're done. Determine the complete solution. 3, negative 2. I'm so used to them giving me just a little bit of space for one problem, so I didn't actually realize that they wanted me to do this part of it here, this part of it here, and then all of these two parts of it down here. It still wouldn't have all fit like these two parts, but we got the whole thing completed. And the organizational little breaks don't matter. We just have to do the whole part of it. Now it would like me to check. Okay. So check. In the original equation, negative 2x, that's negative 2 times 3, plus 5 times negative 2. We are asking, is this negative 16? So let's see. That's negative 6 minus 10. Is that negative 16? And yes, it is. So that's our first check. Second check, 3 times 3 plus 2 times negative 2. Is that 5? So that's 9 minus 4. Is that 5? Yes, it is. So they both check. Sorry for the off screen. All right. Moving on. Substitution method revisited. So we're going to try again. Solve the following system using the substitution method. We need to solve for one of the variables. Okay. So they have given me a suggestion to solve equation 1 for x. So I'll do that. But I do want to note that I do have good choices here. I could solve the top equation for x or the bottom equation for y. Either one of those would have been a logical choice because they both have coefficient 1 or -1, something that's not going to cause a fraction when you divide it off. So I would not have wanted to do those other variables. This x would have caused a fraction. If I divide by 5, I get some fraction there. If I divide by 2, another fraction. So one of those is a better choice. And realistically, this one is the best choice because its coefficient is +1. So it's the easiest one to get by itself. So we'll get it by itself. X minus 2y equals 5. Got to add that 2y over. So we get x by itself equals 2y plus 5. You could have written that as 5 plus 2y, 2y plus 5, doesn't matter. So I chose this order. All right, we're substituting. So we know that this has to go in for x. Right there in the second equation, we're going to plug 2y plus 5 in for x. So 5x becomes 5 times 2y plus 5 equals -2. Oh no, minus y. I forgot the minus y. Not for long though. 5x. That finishes x. I had to put minus y for this part of the equation, right? Then equals -2. Finish the distribute. That's 10y plus 25 minus y equals -2. So 9y, 10 minus 1 plus 25 equals -2. Got to subtract our 25 from both sides. 9y is going to be equal to -27. Divide both sides by 9. So y equals -3. I need to determine the x value, so I'm going to plug that -3 in for y here. So x equals 2 times y, which is -3, plus 5. That's -6 plus 5. That's -1. So the complete solution is -1 for x, -3 for y, ordered pair in order x, y. All right. One more example. Number 7. Solve this system using the substitution method. And then on the next page, solve it by the addition method. So we're going to get the answer both ways to talk about pros and cons of both methods and make sure we're getting the same thing. Okay. I'm solving for x because it has coefficient 1. Y would have been an okay choice if I didn't have a coefficient 1 in x because it has coefficient -1. That's my second choice. I don't have to go with my second choice. I have my first choice. So x minus y equals 5. Add that y because you need your x by itself. X equals y plus 5 or 5 plus y. The order on that doesn't matter. Y plus 5, 5 plus y, don't care. Okay, so that is x. That is going in for x. So now I have 4 times y plus 5 plus 5y equals -7. 4y plus 20 plus our 5y equals -7. 4y and 5y make 9y. Plus 20 equals -7. 9y equals -27. Am I getting deja vu here on this one? It looks like I'm getting something kind of similar to where we were last time, and I get y equals -3. And not done, but I can come back over here and say x is -3 plus 5. So this time x is 2. And so our solution for this one would be 2 comma negative 3. Last time, we're going to do this same problem again on the next page with the addition method. So I got to write up the x minus y equals 5 and the 4x plus 5y equals negative 7. So for x's, 4 and 1, we could use 4. For y's, 1 and 5, we could use 5. They're really both very close. It doesn't matter. What I notice about these is there's a slight advantage to y this time because I need them to be opposites. And there's already a negative and a positive for y, so I don't have to mess with sign, positive and negative, if I choose to get rid of the y's. I could do x's. To get rid of the x, I would just need to multiply these all by negative 4. But I can multiply these all by positive 5, and you have less error if you multiply by a positive than you do with a negative. You often make fewer mistakes. So that's the reason I'm going to choose this one, is because I already have opposites. So we're going to take and multiply the top equation by 5 because that is necessary to create a negative 5y to cancel out with that positive 5y that's there. So 5x minus 5y equals 25 when you finish that distribute. 5 times 1, 5 times negative 1, 5 times 5. And underneath it, we have our 4x plus 5y equals negative 7. And we're ready to add our two equations together. Negative 5y and 5y add to 0. I get 9x equals... hold on. I'm thinking about this one for a second. I don't have the same thing from the last time. So I'm going to have to look for an error there. But 25 minus 7 is 18. Uh-oh. No, this is x. No wonder. I was thinking that I was going to get the 27. I have x. This is still good. This is still good because that gives me x equals 2, and that is what I had last time. Momentarily had a confusion in my mind because we solved for y first. We got y first last time, and I was like, where's my negative 3? But I wanted 2 for x. So I got x first this time. I got 2 for x, and that does match what I had before. So much relief. Now we need the y variable. So I have to take my x and I have to plug it in for x. Does not matter which equation I get to choose. So I'm going to choose smaller numbers. So 2 minus y equals 5. Okay, so if I subtract 2 from both sides, negative y equals 3. Divide off the negative 1 coefficient. Y equals negative 3. And so I do have 2 comma negative 3. And there we are. This question was one where both substitution and elimination, or substitution and addition method, were of equal ease. It did not really matter which one I chose. If it was a case where there were numbers in front of all of these bits and substitution was difficult, then elimination would be better. If you had a variable already solved by itself, it'd be more difficult to put it into standard form for addition. Some questions are more ready for one method than the other. I will also just mention on this one that every one of these is graphable. So if I type in my x minus y equals 5 and my 4x plus 5y equals negative 7, there's the solution sitting right there at 2, negative 3. So we certainly can look at them graphically as well.